Okay, hi everyone. I'm sorry, it didn't allow me to share. Now it does. Okay. Okay, let's see. All right. So any questions? I saw some of them, but I had to come in and out. I saw something about an ebook. Hello, can you hear me? Okay, thank you. Yeah. Yeah, if you have your questions, please put them again. I saw some questions, but I had to come in and out. Okay, thank you. All right. So anything? Yeah, so um, can you get it over Amazon? Is that possible? Because there's no online, but we will upload the copies, upload the first few chapters. There's no online version. Yeah, but he's not here. So he's wondering how else. I don't know. Is there any other way you can order that book? There's no way you can order books internationally. But we will upload the first few chapters. Yeah. And maybe in the meantime, use the 9088. I mean, if you still have problems, make a post on Piazza and we can discuss. I'm not sure yet. I'm talking with Camelia. But in the meantime, you should get the 9088 copy. I will try to get them today. I'll ask Camelia if we can get them today. Okay. All right. So sorry. So we left off on diagonalizable. All right. So last time we just did a review. So let's continue and finish the review and then start on complex numbers. So a matrix is diagonalizable if once you find its eigenvectors, there will be n of them. So they have to match the dimension. And they have to be linearly independent. Okay. No, the 9088, it will just be temporary. I don't know the exact section. So let me talk to Camelia about these things today. I think we can try to get it scanned soon. So, but you should definitely try to get a physical copy of the 2011. Yeah. So let me I will talk with Camille and we'll see what we can do. All right. Okay, so this is the definition for diagonalizable. And last time we did an example, we had this simple matrix, 1, 2, 3, 2. We computed its eigenvalues, -1 and 4. Okay, so this was the polynomial. This is always the polynomial for the 2 by 2 case, so you don't have to memorize. Okay. Also, there's a formula for eigenvectors. I'm not sure if you've seen it before. So that saves a lot of work in trying to derive it. Okay. And let me see any questions. Okay. Yeah, and so this formula is true when C is not 0, when B when C is 0 and B is not 0, you can use the other formula. But when C and B are 0, then you already have a diagonal matrix, in which case it doesn't matter. You just have 1, 0 and 0, 1. So if C is 0 and B is 0, then V1 is 1, 0 and V2 is 0, 1. Okay. All right. So we found these eigenvectors, and that means that you can write the standard representation. Okay. In terms of the diagonalized version of the matrix with its eigenvalues. And this P here is called a change of basis, if you like. Okay. Will it be worthwhile to remember formulas like that, especially for, yes, I mean, I'm sure you remember how painful it was to compute eigenvectors. So I think this will save you time because it's pretty easy to remember, right? You just, for V1, you put lambda 1 and then it's DC. And then same thing for V2. I think it saves a lot of time. If the matrix is diagonalizable, do we all know is that such a matrix P exists, or is there a way to compute it easily every time? Well, right, so this matrix P, I thought I wrote it here. So the matrix P is this guy over here. So you take the eigenvectors and put them as columns. So I should have written it here. So let me write it now. Oh, I did write it. So yeah, this is P. You see? So V1 is the first column and V2 is the second column. Okay, Will? Will, is that okay? Okay, Parth and Will, is that okay? David says on what, oh, what's the eigenvalue and eigenvector of a change of basis matrix? Is it the whole R2? I'm not sure what you mean. This P is the change of basis here. Right, David? So, I mean, maybe the change of basis is not a good word here. But in a way, that's what we're change of basis for this operator T, for T. So this is not going from, you know, I mean, okay, anyhow. So this is the change of basis going from these eigenvectors V to the standard basis, right, David? I don't know what you mean by R2. I mean, so what do the letters next to T represent, like TEE for standard and eigen for diagonalized? Right, so we talked about this a little bit last time. So we have this matrix representation for T, right? So this is TUV. So then T of EE means that you write, it's the matrix AIJ, where you take the standard basis. So, you know, in the 2 by 2 case, 1, 0, 0, 1. And you evaluate this guy in terms of the other ones. So it will be A1, 1, 1, 0, plus A2, 1, 0, 1. Okay. So you do this the same for T01. So A 2, no, 1, 2, and A2, 2. Okay. So this will give you your A11, A2, A12, A21, A22. This is T of EE. And the same thing for VV. Okay, Rudrash? Are all vectors in our two eigenvectors? No. I mean, they have to be linearly independent. Not every vector. If they're linearly independent, yeah, you can try to do that. Yes, the answer is yes. They need to span a space. Okay, David. We can talk about it after more. That's a good question. It's just we can talk about it. Okay, so right, but there's another criterion for diagonalizability, just to make it easier for you to check that you don't have diagonalizable. That's usually how the following stuff is used. So remember that we get our characteristic polynomial. In the 2x2 case, we just had this nice formula with a trace and determinant, but your matrix could be arbitrarily big. So you have this guy over here where k is less or equal than n, the full dimension for m. And these exponents, right, if you remember, they're called algebraic multiplicity. Okay, these are the number of times each eigenvalue shows up in the polynomial. Okay, so in the previous example, we had the determinant of lambda I minus m was equal to lambda minus 1 and lambda minus 4. So m1 is 1 and m2 is also 1. Okay. So that's algebraic multiplicity, and then geometric multiplicity is you compute the space for eigenvectors. So let's see what we have. So E of minus 1. So these are all the x's, so that m of x is lambda or minus 1 of x. And we already found that this is the span of the guy 1, where is it? Minus 3, 3, so minus 1, 1. Okay. And the dimension of that is just a line, right? Of this span. So is that okay? So this is a geometric multiplicity. All right. You simply find the corresponding eigenvectors and you compute the eigenspace. So just to see if you're following, consider the following matrix. Yeah, whatever. So consider this following matrix, and can somebody tell me what's the eigenvalue and the eigenvector? So what's the eigenvector space for E lambda here? Right, and the dimension is, so we have that this is the span of two guys, right? So the dimension of E5 is 2. Okay. Angela says, intuitively, algebraic multiplicity is how many times a root shows up, and then geometric is how many times an eigenvector shows up. Well, it's not quite correct, no. So you're right about algebraic multiplicity, but for geometric multiplicity, we are still looking at the eigenvalue. So we're talking about geometric multiplicity of lambda, not of the eigenvector, right? Because then we ask for the dimension of the eigenspace of that corresponding eigenvalue, right? So we have two eigenvectors. That's why I did this example for one eigenvalue. Is that okay, Angela? So it's always about eigenvalue. So geometric multiplicity of eigenvalue. Is that okay? Okay, good. All right, so then in the notes that you find under the section, they prove this result, namely that a matrix M is diagonalizable if and only if the geometric multiplicities, the exponents, are equal to the sum of the dimensions. Okay, so if you have that, then your matrix will be diagonalizable. And the proof was basically showing that so it was showing that this result implies that V1 to Vn are Li by contradiction. There was some contradiction there that if they're not, there's some dependence and so on. So you can see the details there. Okay. So I see a lot of questions here. How many eigenvectors can one eigenvalue have? Well, in theory, all of them, right? So 5, 5, 5, 5, 0, 0. This is lambda equal to 5, but the eigenspace will be as big as, you know, it can be as big as how many diagonal entries you have. So, 0, you know what I mean. Is that okay, Arya? Rudra says, in this example, both B and C are 0. So like I said a little bit in the beginning, when you have both of them 0, then you just get the standard. So for this guy, you use just the standard basis. It's always the case because it's already diagonal. So one eigenvalue gives you multiple eigenvectors. Therefore, you have geometric multiplicity greater than 1. Yes, exactly. Yeah. So in a sense, it's about the number of Li eigenvectors for an eigenspace. Exactly. Yes. That gives you the dimension of the space because they're the basis vectors. That's how you compute the dimension. But reals are not algebraically closed. They're not. Did I say they were? Sorry, what was it about V1 to Vn? They are. Oh yeah. So just to save us some, I usually write it in short. So Li, just to say linearly independent. Criterion. I'm not sure I understand. So here we are allowing complex eigenvalues, David. So you can see the details in the notes. I think that's what you. Yeah. That's a very good point, actually. Yeah, here we are allowing complex eigenvalues. So this, in fact, will always be equal to n because the complex are algebraic closed. I think that's what you mean. What are the cases when algebraic multiplicity is not? Yeah, so yeah, it will have to be non-diagonalizable. So I don't remember exactly. In the notes, there is an example. So I think it was something like this. And lambda is 5. So it has algebraic multiplicity equal to 2, but it only has one eigenvector, namely, what is it? So C is 0, so I have to use the other formula. So I take, what was it? 5 minus, I don't even remember. I usually use the other one. Okay. So 5 minus B. 5 minus A. Where am I? So, right, 5 minus A. So 5 minus 1 and then B. So let me write it on the side because that's a good question. So the question was, can you give me an example where you have algebraic multiplicity not equal to geometric multiplicity? And here you compute the eigenvector. So you have lambda minus BA and right? did I make a mistake again? Lambda minus a. It's too early in the morning. Lambda minus a b. So you have 5 minus 5 and then 1. So you get 0, 1. And that's the only eigenvector. Okay, so you have dimension of E5 is 1, which is strictly less than the geometric multiplicity. Is that okay, Sakura? Okay, great. All right. All right. So yeah, in the previous example, I already talked about that. It was 2. Oh, I'm also doing examples here. I see. Yeah. So this is the example I was talking about. Here you have a dimension of E5 is 1, which is strictly less than the algebraic multiplicity. Yeah, so I talk about that here. Oh yeah, but just to serve as a teaser, this is already in a good form. This is upper triangular, and in applications, that's often all we need. So in the last week, we will talk about how to bring a general matrix M into a form of upper triangular. Okay, so that would be like the intuition for, that's the teaser for Jordan canonical form. Yeah, you could have the same eigenvalues, or multiple eigenvalues yielding the same eigenvector. By multiple, I'm guessing you mean distinct, in which case, no. If you have distinct eigenvectors, eigenvalues, you get distinct eigenvectors, right? Because remember, the statement is AV is equal to lambda V. So if you have it for the same, then you get a contradiction, right? Because when you take their difference, you get lambda 1 minus lambda 2V is equal to 0. But I'm assuming this is not 0. So you get V 0. Okay. Mayma says, will it be 1, 0? Because C is 0. Yeah, C is 0. Yeah, but I used the other form. Maybe you should check me on this. Sorry. I think I wrote it here. Yeah, 1, 0. The thing I wrote here is the correct one. So yes. Did I write? Let me fix it here. Yeah, okay. Thank you. So this is the other way. Thank you. So B lambda A. So you get 0, you get 1, 0. Okay. All right. So okay, that's for the review, and now we move on into complex numbers. Okay, so let's start there. So what's a good introduction is the rotation matrix. Okay, so this is called rotation matrix, meaning that if you have a vector like this with an angle phi, let me go in the picture. So if you have a vector, I call it xy, so v over here, and you multiply v by this r theta, then you get another vector r theta v whose angle is theta plus phi. So it will be theta plus phi. Okay, so it shifts the angle of your vector with respect to the x-axis. Okay, so that's what the this rotation matrix does. I gave details on how you compute all the angles and stuff. But let's work with a specific example because this is a little bit too abstract. So let's look at when you take your vector v and you move it by 45 degrees. So let's say it goes up here. Okay, so it goes from here to here, 45 plus phi. All right, so this is the R1 V. All right, so this is our matrix. This is the R1. And let's find the eigenvalues. Let's find the eigenvectors. So, okay, I mean, I'm not sure if you can give it a try. So this is a 2x2 matrix. If some of you are comfortable with the eigenvalues, does anybody have an idea? So remember, lambda square is trace m, and then lambda plus determinant of m. If you want to practice, does anybody have an idea? I'll give you a few seconds. So at least, oh, 2 minus 2. Let's see. So what do you have? You have lambda square. Trace is the sum of the diagonals, so 1 plus 1. And then determinant of m, right, okay, there we go. Then determinant of m is 1 times 1 and then minus 1, so you get another 2 here. Now, if you try to compute the roots of this polynomial, you get what Parth said. You get 1 plus minus 1 of square root minus 1. So we realize that many of you have not seen complex numbers. I mean, it's not in the prerequisite courses. So we have to talk about this square root of minus 1, how to make sense of it. Okay, and that's fine. So the eigenvectors, again, we use our formula because C is not 0, right? This is C, it's 1. So these are our two eigenvectors, okay? And again, this square root of minus 1 shows up in there, and how to make sense of it, how to work with square root of minus 1, right? Because so far, whenever you've seen square root, the condition was that x needs to be bigger or equal than 0 from calculus, right? That's how we did calculus there. Oh, I see. Great. So, okay, so this is the situation. What the hell is this square root of minus 1? All right. And then, okay, you found the eigenvectors, you do your diagonalization, but then on what vectors does it act on, right? So this P will be square root minus 1, 1, minus square root minus 1, 1. And what kind of vectors does it act on, right? So what will V be? All right. So yeah, this is the motivation that in a real problem, there are no complex numbers here. Complex numbers showed up. Okay, so that means that to solve real problems, we need to come up with complex numbers. I don't know, if you've done a bit of calculus, you might have seen even like real integrals like sine xx. And to find that this value was, I think, pi over 2 or something, you need to use complex methods. So that's a recurring theme, that in real problems, it's very helpful to use complex methods. Here they use contour integration. All right, so let's talk about, let's talk about complex numbers. So you should think about this as a new field, a new area. You learned about real numbers. where you have minus infinity, infinity, and you have, your minus 1, 1, and so on. Now we define a new object. Okay, you should really think about this as a new object, because square root of minus 1 is not a real number. It doesn't make sense as a real number. So we really have to work with this new object called complex numbers. And basically you start by setting this square root minus 1 that gave you trouble to be a symbol, I. That's how we define it, just to do calculus with it. And as you can see, I squared is equal to what? Square root minus 1 squared, so minus 1. So this is surprising, right? Because in calculus, you always have that x squared is positive. But here, z squared could be negative. Okay, so because it can contain this I squared, right? So if you take like z equal to 3i, then z squared is equal to minus 9, which is negative. Okay, so that's the intuition for complex numbers. You can represent them geometrically. So if you have a complex number of the form x plus iy, you can put the imaginary on the top and real in the bottom. So let's do an example like 5 plus 4i. How do you do this? Well, you look at the real part, it's 5, and you look at the imaginary part, it's 4. So then this guy is your complex number. Okay. All right. Hopefully that. How would you represent them in higher dimensions where you have more choices to assign as imaginary? That's a very good question. We will come back to CN very shortly. Yeah, we'll come back. Yes, that's a good question. We'll come back. All right. So yeah, so this is real and imaginary. What else? We introduced some other things. We introduced the radius of this modulus. So modulus of z, we define it as the square root of its x and y component. So let me do an example on the right here. So if you want to find, let's say 1 plus 1 I, what do? You take this guy, 1 squared, then you take the other guy, 1 squared. So you get square root of 2. Okay. What's the difference? Yeah, exactly. This means definition. So when we say I is defined as this, we mean that's how we make sense of square root minus 1. Okay. Yeah. It's like when you use a variable, you say like, x equal to 4, meaning that from now on, whenever we work with x, it will just be 4. I know this is a silly example, but that's basically the idea. Okay, and then, but what does this radius represent? So let's do an example, is just this distance. So this distance here from the origin represents the radius, the modulus. Okay, so if you've seen it before, this is called the Euclidean distance. Okay, that's because we can identify complex numbers, so z equal to x plus iy, with the vector going from 0 to xy. So, okay, any questions? That's also called the norm of z. That's right. Yes, also norm. Yep, perfect. All right. And moreover, we have the notion of angle. So this angle with the x-axis, theta, we call it argument of z. In practice, we don't really use arctan to compute it. This is the definition, but this is quite awkward to work with this for computing the angle. So there's another way to do it, much more convenient. So is what is called the polar form. So if you have a number like a complex number x plus iy, you can write this the following way. You can write it as the modulus times its position on the unit circle. So cosine theta plus I sine theta. So why is that possible? So suppose z has norm 1, okay? Then it means it's somewhere on the unit circle. So like over here, right? So this is z equal to 1. But hopefully you remember from calculus that any point on z equal 1 can be represented as some cosine theta, sine theta, right? For theta between 0 and 2 pi. So you give me any point on the unit circle, I can find you an angle. I can find you the angle with the x-axis. Then by putting in those two values for cosine and sine theta, I can find you the exact location, right? So if you give me the angle, I can give you the location of the vector. Does that make sense? So, you know, just as like a silly example, you know, take z to be I, okay? Then pictorially, this is this guy over here, okay, that has 90 degrees, okay? So this is I. And yeah, so let's find the polar form of I, okay? So polar form of z equal I, you give me the angle, then I know that since the modulus of z is 0 plus 1 squared, so 1, I know I can just, based on the angle, give you the exact cosine sine theta. So you have 1 times cosine of 90 degrees plus I of sine of 90 degrees. And cosine of 90 is just 0. So we get back the same thing, but it just shows you that you can write it as in a cosine sine form. Okay, that's right. Yeah, it's pi over 2, exactly. Daughter with 0, 1 and use Arcos. Sorry, 1, 0. Right, yeah. I mean, yes, yeah, I should start asking you guys. You guys know a lot, so I shouldn't be doing this all by myself. So yeah, there are many ways you can find these angles. And so this is the polar form. We'll do more examples right now to give you some idea. And finally, I should also introduce the complex conjugate. So pictorially is as follows: complex conjugate. So you give me a vector z. Once you reflect it across the x-axis, you get z bar. And the reason is because this guy is x plus iy. And z bar is equal to x minus iy. So you reflect across the axis to get the negative imaginary part. Okay. One reason this is interesting is because if you take their product, z and z bar, you get the following. So I'll do it by hand now, but in the future, we'll just write it. So you have x squared, you have x times minus iy, you have iy times x, and you have iy times minus iy. Let's clean this up. X squared minus yx plus iyx, and then I squared y with minus 1. These two guys cancel out, right? Same term, but with minus. I squared becomes minus 1. And minus 1 gives you 1. Okay, so that's the formula. You have that z bar is equal to x squared plus y squared, which is just the modulus squared. Okay, that's a very useful formula that we will come back to it. All right, is the complex conjugation only for a y-axis reflection? No, x-axis reflection. Isn't this the x-axis? You're reflecting across the x-axis. Yeah, y squared, yes. So you can factor x squared, y squared. Yes, exactly. You can, I want to say the factor, you can be left with, yeah, okay. All right, let's do an example. So we found these eigenvalues for our rotation matrix, 1 plus I and 1 minus I, when we computed the roots of the characteristic polynomial. And yeah, and note they're conjugate of each other because you have plus and minus and same real part. So first we find the modulus. So you just add the real and imaginary part. Okay. So you get square root 2. And yeah, can somebody tell me what's the modulus of 1 minus I? Yeah, okay, thank you. Perfect. Nice. Good job, guys. Is there a y-axis reflection? I will have to think about this. I think there is. Yeah, there is one, but I have to think a little bit because what it says is you have this and you shift the angle like that. So basically you moved by 90 degrees. So yeah, you have to multiply by pi over 2. I mean, okay, I'm getting ahead of myself, but yes, there is a way, Kellyanne. We can talk about it, yeah. When we say that arczen is arctan of x, do we need to manipulate the angle on our own four coordinates in second and third coordinate? I'm not sure what you mean manipulate the angle. The angle is given for every complex number, so we're not allowed to play with it. Also, I will advise not to use the arctan. I know I wrote it, but it's better to use the polar form. Arctan has a split definition, so it's very hard to work with. All right. So yeah, namely here, let's find the angle, the argument for 1 plus I. I mean, pictorially, you can right away see it. So this is 1 plus I. And it splits it exactly. So you get 45 degrees, but let's find it mathematically here, symbolically. So the way I do it is I want Z to equal R cosine theta plus I sine theta. So there's a beautiful thing about complex numbers that you can equate them. Okay, so here's the thing that we're using. So if you have A plus IB equal to C plus ID, you get the following system. You get A is C and you get B is D. Okay, so, okay. So we use this system to get this system over here. Namely that we set 1 plus I to equal modulus of z cosine theta plus modulus of z I sine theta. So we get 1 is equal to square root of cosine theta, and then 1 is equal to square root of sine theta. And from here it's easy because here we use the table. So use the trig table. Okay. So that's what we do here. All right, so I will continue a little bit on complex numbers tomorrow. There's not much left, and we'll introduce the fields. Okay. So no, we're fine. We're good. Yes. Okay. So thank you, everybody. We'll continue tomorrow on complex numbers. Thank you. Thank you, guys. So if I see some people are left, if you have questions, just let me know. I can answer. David, if square root of -1 is a contradiction, how can we redefine it? Well, that's the thing. I shouldn't use the word, like if you work in real numbers, then yeah, you can really, you can do calculus, real calculus with square root -1. How do I move here? So, oof. Yeah, so yeah, you cannot do real calculus with square root of -1. You know, for example, in real calculus, you know that x squared plus 1 is strictly positive, right? That's what we say in real calculus. But if you allow x to be square root -1, you get that this guy is, you know, square root -1 squared plus 1, you get 0, which is a contradiction. So you can only do real calculus with it. So we introduce this new space of complex numbers. So this is really like a different object altogether. Can I take any proposition that is proved false and claim it's true altogether? Well, let me see. If it's interesting, that's right. Yeah. If you can get something interesting out of it, yeah. The reason we use this is because for one thing, it contains the real numbers. So, you know, when you write a plus ib, a and b are real. So it does contain the reals, right? So it's not like you still have consistency. Okay. So you still have consistency, meaning that stuff you do with complex numbers contain what you can do with real. And so often, yeah, you can turn real problems into complex, like the one I mentioned, sine x over x from 0 to infinity. You can turn this into a problem in the complex plane. Then no proof no, I mean, that's funny. Well, we have consistency though, right? So it's not like that you cannot still say this. Is that you have to be careful. You have to say this is true when x is real. And this is true when X is allowed to be complex, like, when X is like minus, when X is I. So you have to be careful with your domains. Yes. So, and also the domain, you always have to specify the domain. So you should think about this as a new domain. So you have, you have reals, and then you extend, and the extension is consistent. Meaning that you can still say that x squared plus 1 is strictly positive when x is of the form A and B is 0. So there's this consistency there. Is that okay? Okay. Okay, so if there's no other questions, I think, all right, okay. Thank you guys. I'll see you on Friday.